A smooth sphere A of mass 2m moving with speed u collides directly with a smooth sphere B of mass 7m, which is at rest. B then collides with a vertical wall which is perpendicular to the direction of motion of the spheres. The coefficient of restitution is a half for all collisions. Show that the spheres will not collide for a second time. Okay, so here's the picture. Immediately after collision, the velocities of the spheres have to be determined. And I don't know what the directions are, but the sign will give us the directions. Vectors pointing to the right have positive sign. That's the convention that I will use. Now, the resultant external force on each of these spheres is 0. The spheres may be near the surface of the Earth, so there's a gravitational force on sphere A, which is vertically down. But since sphere A is resting on this surface, we have an equal but opposite contact force on sphere A due to the surface. So the sum of these two forces is 0. Also, we are assuming that the sphere is so perfectly smooth that there is no friction force on the sphere due to its moving along this surface. So there's no force pushing back on the sphere. So that means, by the way, that the sphere doesn't roll. The sphere will actually slip along this surface, and this point will always be in contact with the surface. So I explained all that stuff in the previous video. Okay, we can go and apply conservation of momentum. So we want the total momentum before the collision. So that's the mass of sphere A times its velocity, which is u. Now you can put an arrow over u if you like, but if you leave off the arrow, this is fine because u is the speed. So a speed is the magnitude of a vector is positive, and I've set things up so that the velocity vector is positive. So the initial velocity of u is positive. We could write it over here. The initial velocity of A, I should say, is equal to u, and since u is a speed, it means it's a positive quantity, and that's what we want. Directions to the right are positive. Sphere B is at rest, so its momentum is 0. Now let's get the momentum after the collision. So the momentum of A is 2m times its velocity, which we don't know, plus the momentum of B is its mass 7m times its velocity. So notice here that the value of m does not matter because it cancels all the way through. So we could take the mass of this sphere to be 2 kilograms, which means that this one is 7 kilograms. Or we could take this mass to be 4 kilograms, so we would have to make this one 14 kilograms, as long as the ratio is 2:7. Okay, this fact is just more of an aside. Now there are two unknowns, VA and VB, in this equation, so we need a second equation obviously, and here's the equation that involves the coefficient of restitution. So in any impact, the relative velocity after the collision is proportional to the relative velocity before the collision, and the directions of the relative velocities are opposite each other. So the velocity of A relative to B is opposite the velocity of A relative to B before the collision. E is a half. The initial velocity of A before the collision is u. Okay, we had that up here. The initial velocity of B before the collision is 0 because B is at rest. So here's our second equation of VA and VB. Notice that we're not going to get values for VA and VB. When we solve between these two equations, we're going to get VA and VB in terms of u, the initial speed of sphere A. So we just combine these equations in the usual way to eliminate either VA or VB. So I will eliminate VA. So I'm going to write the second equation in here. So I've doubled this equation. And just add these together. By the way, I want to multiply this one by -2. So we end up getting that the velocity of sphere B immediately after the collision is 130. It's positive. So sphere B is moving to the right. Okay, that's obviously not surprising. Okay, now let's get VA. So from this equation, add VB. Notice that VA is negative. U, remember, is positive. It's the speed. It's the speed of a quantity. It's the speed of sphere A. Well, it doesn't matter what it is. It's a speed. If it's a speed, it's a positive quantity. It's the magnitude of a vector. But it's minus 1/6 times a positive. So obviously VA is negative. So if we go back up to our picture here, we can see that since directions to the right are positive, VA must be negative. Sphere A must move to the left. Its speed is minus 1/6 u. Its velocity is minus 1/6 u. Okay, what we need to do next is to get the velocity of sphere B immediately after it collides with this wall. So here we're dealing with a single particle collision. The velocity immediately after impact is proportional to the velocity before impact, and they have opposite direction, obviously. So we multiply by negative scalar. Okay, so E is a half, and the velocity immediately before impact is 1/3 u. Remember, this sphere keeps travelling forever with speed 1/3 u until it hits this wall. You know, there are no forces acting on it, no external forces, well, apart maybe from gravity and this contact force, but the resultant external force is 0, so that means the acceleration is 0. So the speed is constant. Okay, so we get minus 6 u. So now pretend that I'm showing sphere B after it has collided with this wall, so it's moving to the left, obviously, that's no surprise. But notice that its speed is the same as the speed of sphere A, but sphere A started moving to the left before sphere B did, so obviously sphere B can never catch up with sphere A. As a matter of fact, the gap between the two spheres will be constant because they're moving with the same speed. Here is a simulation. The elasticity, or the coefficient of restitution, is set to a half. Now we want the masses to be in the ratio 2:7. So you can make the first mass 2 and the second mass 7, or indeed I could have made this 4 and the second mass 14. It doesn't matter, as we saw. The mass cancels out. Also, we saw that the speed can be any value we like, the initial speed of sphere A, because the final speeds are minus 1/6 u and minus 1/6. They're the same, so it doesn't matter what we set for the speed of the sphere. Now I've set it to 1 meter per second. So we can see here that the speeds are the same. Let's see the simulation again. This time I've changed u, the initial speed of the first sphere, to be 3. Again you see that the final speeds are the same, so the second sphere will never catch the first sphere. Okay, in part 2 we need to get the initial and final kinetic energies. So we need the speed of sphere A. Well, that's just u. We need to square the speed. And here's the final situation. The speed of each sphere is 1/6 u. We disregard the sign when we're looking at the speed. But it doesn't even matter if we put in the minus sign because we're squaring anyway, so it's going to be positive. Okay, kinetic energy is a scalar quantity, so it involves the scalar speed squared. So you can see that the kinetic energy goes from a value of mu squared down to 1/8 mu squared. So the change in kinetic energy is 1 minus 1/8, which is 7/8 mu squared. So again, as a reminder, if E is less than 1, as it will be in all the problems that we do, we have what's called an inelastic collision, and we always have a loss in kinetic energy. So the kinetic energy after will always be less than the kinetic energy before. In the ideal situation where E is equal to 1, we have what is called elastic collisions. In that case, there's going to be no loss in kinetic energy. So the kinetic energy before initially will equal the kinetic energy finally. A smooth sphere A of mass 3m moving with speed u collides directly with a smooth sphere B of mass 5m which is at rest. The coefficient of restitution for the collision is e. We want to find the speed in terms of u and e of each sphere after the collision. So I assume that there's no external forces acting on these spheres, or if there is, the resultant external force in each sphere is 0. Okay, so let's get the momentum before. So the velocity of sphere A before the collision is u. Okay, u is going to be positive. I'm taking directions to the right as positive. And the momentum of sphere B is 0. Speed is 0. And let's say that the velocity of sphere A after the collision is VA and the velocity of sphere B after the collision is VB. So you see that m's cancel out. So all that matters is the ratio of the masses of these two spheres. Actually, the ratio, as you can see, is 3:5. Okay, so here's the picture after the collision. Now, I don't know what the directions of VA and VB are. Well, they're going to depend on the value of u and also on the coefficient of restitution e. And actually, we're not given values for u and e, so this is going to be a very general situation. So the next thing we do, of course, is consider the relative velocity of, say, A with respect to B after the collision, and that's proportional to the relative velocity of sphere A to B before the collision. Okay, the initial velocity of sphere A is u. It's positive because u is the speed, and the speed is a positive quantity. Okay, so that's why I put the arrow pointing to the right, so that I can write down the speed of A before the collision as u. Now if I put the arrow going the other way, pointing to the left, I'd have to stick in a minus sign here, because u is a magnitude, it's a speed, it's always positive, so I have to be consistent. Alright, so the initial velocity of B is 0. So I have to solve between these two equations. I want to get VA in terms of u and VB in terms of u. So if I multiply this by 5, choose 5 because I'm going to cancel the VB's by adding the other equation onto this equation. So add this one in here. Okay, gather these two together. You can factorize, when you add these together, you can factorize out the u, and you'll end up with VA. Now notice that the direction of VA could be positive or negative, depending on whether this quantity is positive or negative. Now we already know that u is positive, because it's a speed. So if this thing is positive, well then VA is obviously going to be positive. So if we go back to the picture, if VA is positive, then VA is moving to the right. But of course this thing here in front of you could be negative. Depends on what E is. So if the thing in front of you is negative, well then VA is going to be negative. So in that case, sphere A is going to rebound and move to the left. So you see, everything hinges on what E is. Now E is a number between 0 and 1. So we could make all this thing positive if we want by choosing the right values for E, or we could make it negative. Anyway, let's go and get VB now. So I'm using this equation here. So add on this quantity. I could get a common denominator of 8, but I'd have to stick an 8 up here. Just multiplied into u here. 8eu minus 5eu is 3eu. I could factorize 3u out of the top, and I could take out the 8, and in brackets here I could write e plus 1. Incidentally, notice here that this thing is always positive, because e is always a positive number. E is always between 0 and 1, of course. Depends on the materials that the spheres are made out of. u is a positive number, so obviously this thing is all, and that's no big surprise, of course, that VB has to turn out to be positive. Okay, because sphere A collides with sphere B, and sphere B obviously moves to the right. Find the value of E if the magnitude of the impulse imparted to each sphere as a result of the collision is 2mu. Now we saw in a previous video that the impulse imparted to, say, sphere A is just a change in momentum of sphere A. Okay, so that's the momentum just after the collision, which is its mass times its final velocity, VA. Well, here's VA. Minus the momentum just before the collision. Well, its velocity before the collision was u. Now we saw that because of Newton's third law, these two quantities are the same. Well, the magnitudes are the same. The impulse imparted to sphere B is the change in the momentum of sphere B. So it's just a force on sphere B due to A multiplied by the time taken. Okay, so that's what we're getting. So that's what we saw in the previous video. And here we're getting the magnitude of the force on A due to B times the time taken for the collision. These times are the same, of course, and we don't know those times. It's some tiny fraction of a second, but this quantity has the same magnitude as this quantity by Newton's third law. Opposite direction, but same magnitude. So we only have to look at one of them. So I'm looking here at sphere A. Okay, so we have to remember, of course, that because impulse is a vector quantity, this thing in here could be positive or negative. There are only two directions to consider, positive or negative directions. And you know, this quantity is positive, it's a magnitude. Well, u is positive, it's the speed, so obviously 2mu is positive. Okay, so we have the magnitude of this quantity. Now, this thing here is positive. But what about this thing? Well, this thing is negative, because E is positive. So, you know, the magnitude of a product is the product of the magnitudes. So the magnitude of this thing is just itself because it's already positive, but the magnitude of minus 1 minus E is plus 1 plus E. We just change the sign to make it positive. So we end up with this equation. And hence we find E. A smooth sphere P of mass 3m moving with speed u collides directly with a smooth sphere Q of mass 13m which is at rest. Sphere Q then collides with a vertical wall which is perpendicular to the direction of motion of the spheres. The coefficient of restitution for all of the collisions is E. So first we want the speed in terms of u and E of each sphere after the first collision. So, as I've mentioned a few times before, we assume that the resultant external force on each sphere is 0. That's before, during and after the collision. Of course, there are external forces on these spheres. If they're near the surface of the Earth, we've got gravity, but as I've said several times before, that's counterbalanced by this contact force. So the resultant external force on this sphere is 0. There's no friction either, because the surface is rough, so as I've said several times, the sphere just slips along the surface. There's no friction force here. That arrow's not meant to be there. And the same is true for Q. So the resultant external force on the system, where by system I mean just the two spheres, is 0. So I'll take directions to the right as positive. So that means that the velocity of sphere Q, the initial velocity, is u. Okay, u is the speed, so u is a positive number, and you know, if we take directions to the right as positive, it means that the initial velocity of p is positive. So the momentum of p before the collision is 3m times u. The momentum of q before the collision is 13m times 0, so the momentum is 0. So that's the total momentum before, and the total momentum after is, for p, it's the mass of p, 3m, times its velocity, immediately after colliding with Q. We call that velocity Vp. And the momentum of Q is its mass 13m times its velocity immediately after the collision, the first collision. So next we apply Newton's law of elasticity, which states that the relative velocity immediately after the collision, Vp minus Vq, is minus e times the relative velocity of the spheres just before the collision. Now, the initial velocity of sphere P is u, and Q is at rest, so that's 0. Alright, we solve between these two equations. We want to get Vp and Vq in terms of u. U is the initial speed of sphere P. So I've multiplied this equation by 13 and added it onto this equation up here. Okay, so there we have it. The velocity of P immediately after the first collision. So here is sphere Q. Q is move after the first collision. Of course, Q has to move to the right. That's obvious. Now, what about P? Well, P moves to the left or right depending on what the value of E is. Okay, so the final velocity of P could be positive or it could be negative. Okay, U is obviously positive, so you can see that everything hinges on this expression in here. So if 3 minus 13e is positive, well, Vp would be positive and P will move to the right after the first collision. But what does this mean? What value is E? Well, if we do some rearranging here, subtract 3 from both sides and divide both sides by minus 13, so the greater than becomes less than. Divide both sides by a negative. If E is less than 3 over 13, this is the situation. Vp is to the right. You can see obviously that if E is less than 3 over 13, then P is moving to the left. But it's a certainty that Q must move to the right. So we're going to go now and get VQ, and that should come out to be positive. So we plug what we got for Vp into one of the two equations, so this is the easiest one. So I've made Vq the subject of this. So for Vp we plug in u over 16 times 3 minus 13e. We get a common denominator of 16, so we have 16/16 EU and we have minus 13/16 EU over here. 16 minus 13 is 3. We get 3/16 EU, and then we have 3u over 16. Of course we can get our common denominator. We can also factorize 3u out of the top. 3u into e plus 1. Okay, so you can see clearly that this thing is always positive, no matter what E is. E is a positive number between 0 and 1. U, the speed, is a speed, and a speed is always positive. So this thing is always positive, and of course that makes sense. So Q is heading towards this wall. It's going to bounce off this wall, of course, and move left. So we use Newton's law of elasticity. It's the same coefficient E for all the surfaces. So we know that the speed immediately after rebound is E times the speed just before. Okay, so we have to multiply E by the speed just before. Well, here's the speed just before. So it's E times this thing. So that'll give us the speed now, not the velocity. Okay, if we want the rebound velocity, we just put in the minus sign. Now, you know, this just is the formula V equals minus E times U, but I didn't want to write it down because I don't want to confuse the speed after rebound with the speed of the sphere just before rebound, because I used V for the speed just before rebound. So anyway, you just multiply by minus E, the rebound velocity. So the minus sign takes care of the direction. So whatever direction this vector has, we multiply by minus e, we reverse the direction, because minus e is always negative. So anyway, clearly this thing is less than 0, no matter what e is, because we said that this thing is always greater than 0, which makes sense. E is a positive number, so by minusing it, this thing is always negative. So that makes sense, of course, because sphere Q has to move to the left. It has to strike the wall, because it had some speed to begin with, and it keeps going with that speed forever until it hits the wall, of course, no matter how far away the wall is. When it hits the wall, it rebounds and keeps going with this constant speed forever until it hits, if it hits sphere Q. Okay, so I'm looking at part 2 of the question now. We want the range of values of E for which there will be a second collision between the spheres. Now we said that P could either be moving to the right or the left, okay, depending on whether, what this thing in the brackets is doing. So let's take case 1. Case 1 is where P is moving to the right after the first collision. So here's the picture. Now collision is a certainty here, obviously. So we kind of went through this already. So we put this quantity u over 16 into 3 minus 13e greater than 0, and we saw that that's the same thing as saying that 3 minus 13 is greater than 13e is greater than 0, because this u is always greater than 0, this bit here. So we can forget about this bit, that's always positive. So we just need the thing in brackets to be positive. So this means that e is less than 3/13. Okay, so if e is less than 3/13, well, there certainly is going to be a collision between the two spheres, because then Vp will be positive. P is moving to the right. Now let's take the other case. Okay, so now P is moving to the left. So what's going to be the condition on E for Q to catch up and collide with P? One way to think about this is to consider the speeds. Okay, so we want the speed of Q to be greater than the speed of P. So the magnitude of this velocity vector has to be greater than the magnitude of this velocity vector here. So what's the speed of Q? Well, we just dropped the minus sign. So we get 3eu over 16 times 1 plus e. And we know that this is going to be positive. E is a positive number. U was a speed from the first part. It was at the initial speed of P actually before the first collision. So that's positive. So clearly this thing is positive. So we have to make sure that if we're talking about speeds that the quantity is positive. Okay, so that's the speed of Q. Now the slightly trickier bit is the speed of P. Now here I've written down the velocity of P. This is a vector. Okay, and the velocity of P is negative. Okay, we're just assuming that it's negative. Actually, we know that if it's negative, then E is going to be greater than 3 over 13. That's the consequence of it being negative. We saw that earlier. If we set this thing to be less than 0 and solve the inequality, we get E greater than 3 over 13. It's just the reverse of the other inequality when Vp was greater than 0. Okay, so anyway, we're pretending that Vp is negative. Okay, P is moving to the left, so that means E is greater than 3/13. This is going to be negative. We want to make it positive because we want to consider the speed of P, the magnitude of the velocity. Speed is always positive. So we just minus this thing. Okay, so we can multiply both sides by 16 because 16 is a positive number. It won't affect the direction of this inequality. Now we get a quadratic equation in E, and we can divide this quadratic inequality in E, and we can divide this quadratic inequality by U because U, remember, is a positive number, so it won't affect the direction of this inequality. So one way that we can solve this inequality is to consider the graph of this expression. So I'm calling it y, and it's a quadratic function. The square term is positive, so it's an upright parabola. If we set this equal to 0 and solve, we can find where the graph crosses the e-axis. Okay, if you solve the equation, you'll get e equals a third and e equals 3. So we are interested in the range of values of e that make this quadratic positive. Well, you can see that here's the range that we're interested in. E running from 0 up to a third. E cannot equal 3, of course, because we know that the maximum value that e takes is 1. E is a number between 0 and 1. Okay, e can't be negative either, so it's really only this portion of the graph from e equals 0 to 1 that we are interested in. And we're interested in the range of values of e for which this expression is, or y is positive. So for all these values of e in here, y will be a positive number. Okay, so we have two ranges. One range for the situation, for this situation here, and the range from the previous part. Remember where p was moving to the right, this range here. But actually this range of values is included in this range of values over here, because 3/13 is actually less than 1/3. So this range here covers both cases. So the first case is where e is less than 3/13. I'll just show that in blue. Here's e less than 3/13. Of course, more fully, this range is 0 less than e, because e is always positive, of course. Okay, so here's the in blue we have the first case covered. Okay, this one here. Now what about the second case? Well, the second case, remember, the second case is where p moves to the left. When Vp is less than 0, we found that e has to be greater than 3/13. Okay, I'll show this in green. So in the second case, e is greater than 3/13. Well, that's this region in here. So we found that e is greater than 3/13. That's just a condition for this p to move to the left. But for q to catch up with it, e has to be less than a third. It has to be between 3/13 and 1/3. So when e is in the blue region, p moves to the right, and there's certainly going to be a collision. And when e is in the green region, lies between 3/13 and 1/3, p is moving to the left, but q catches up with p. And if we take values of e between 1/3 and 1, well, in that situation q will not collide with p. So obviously p is moving to the left faster than q is.